Welcome to Study Loop.
Hello everyone, today we're doing chapter 17, problem 52. So this problem asks us to use the inscribed polygon method to show the pattern of molecular orbitals of these three structures, one being the cation, one being the radical, and one being the anionic form, and label them as aromatic, anti-aromatic, or not aromatic. So the inscribed polygon method is, so we draw our molecule like this, but we draw it such that the vertex is pointing down. So let me just actually spin this around so that now the vertex will be pointing down in all of these three molecules. So now you see the vertex now, so the vertex is the point is facing down in all three of these molecules. So now the point is facing down, what you need to do is draw a circle around the perimeter. And every time a circle touches a vertex, let me do that in a different color. So every time the circle and a vertex touch, you need to draw a line next to it. So I'll do that for all of these. So let me draw a better circle. So this is a much better circle. So now, at every time the vertex and the circle touch, we draw a molecular orbital. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And we will do the same for all of these. One, two, three, four, five, six, seven, eight, 9. All right, so we drew all the molecular orbitals. Now we need to define which ones are the bonding and anti-bonding molecules. So we just cut the molecule in half. And each one we just cut it in half. Just cut it in half. And now the top is the anti-bonding orbital. So we have 4 anti-bonding molecular orbitals. And then here we have 5 bonding molecular orbitals. And what we need to fill inside these molecular orbitals are the pi electrons. So here, let's count our pi electrons. So we have 2, 4, 6, 8 pi electrons from the alkene double bonds. So now let's start filling the molecular orbitals using Pauli's exclusion principle from the lowest energy to highest energy. So remember, we got to fill each one on the same energy level before we can fill it completely in. So we have 2, 4, 6, 7, 8. So we have 2 empty or half-filled bonding molecular orbitals, and we have 8 pi electrons, and we know that follows the 4n rule, so we know that is an anti-aromatic compound, this cationic version of this molecule. What about the radical? Well, now the radical, we have those 8 pi electrons from the alkene double bonds, but now we have that extra radical electron to include. So now we have 9 pi electrons. So remember, filling from lowest energy to highest energy, making sure we follow the exclusion principle. We see that now we only have 1 molecular orbital that is unfilled, and this doesn't actually follow the 4n rule. So this is actually not aromatic. So it's not aromatic, it's not anti-aromatic because it doesn't actually follow the 4n rule. Well, what about the anionic form? So on top of those 8 pi electrons, we have an addition of 2 electrons that are from this anionic carbon. So we have a total of now 10 pi electrons. So we fill in the molecular orbitals 2, 4, 6, 8, 10, we actually fill every single bonding molecular orbital up. And if we actually follow the 4n rule, we confirm that this is actually an aromatic compound. So not only we confirmed from the 4n plus 2 rule, but we also see that every single orbital of the bonding molecular orbitals are completely filled. So we know that this molecule is going to be aromatic.